Recently, I've been reading this book. It's called Introduction to Plasma Physics by Francis F. Chen, and I specifically ordered the 70s version of this book because it's just so pretty. This is the first edition. Mine was printed in 1976, and you can totally tell. Just look at it. It's gorgeous. I love the font in this book. I love the simple diagrams instead of I feel like textbooks have some really, really ugly color pictures. There's too much color. You can't just throw arts away. You really need an artist to come in and help you design your textbooks so that they look like this. Literally the prettiest, most visually appealing textbook I've ever seen in my entire life. But also, you don't really need to get the most updated version of an introductory plasma physics book because they're all going to have the same basic concepts in them, and they're all going to end with in 10 years, just you wait, we'll have nuclear fusion. So they said it in 76. I'm sure the 2010 version says the same thing, so I'll just pretend in 10 years we'll have nuclear fusion. Just you wait. So you have to study plasma physics because in space, most of the stuff you see is plasma, and we don't really deal with plasma much on Earth. Just a basic definition, because plasma is very complicated. Plasma is ionized gas. So you have a bunch of electrons floating around, you have a bunch of ions floating around, and you have some percentage of neutral matter floating around. Like I said, we don't really deal with plasma on Earth. If you think of something like water, and you want to describe its motion, you only describe the bulk properties of the liquid. You don't really concern yourself with what individual water molecules are doing. The motion of the water is what you're studying. And then you could compare that to gas, where the individual motions of the individual particles inside the gas become really important because you would describe it by its collision rate. That's how you would describe its temperature and things. Plasma is weird because both of those things become important depending on the time scale and the length scale, and because you also have ions and electrons just floating around, magnetic fields become very important. And that's why we want to study plasma in labs. It's not just nuclear fusion. We want to understand what's happening in space, so we need to understand the behavior of plasma. But that doesn't matter because that's not what we're doing today. Because today I wanted to do coffee and the problem. Where's the coffee? So on Coffee and the Problem, we have coffee and I solve a problem. And the idea is it's like a cozy weekend morning, and you pull out your notebook and you solve the problem right along with me. I will give you time to pause and look at the problem so you could solve it yourself if you wanted and compare your answer to my answer if you want to. That's the game. That's the fun. Let me read the problem to you. So we are solving problem 4-22, which is on page 133 of my edition of this book. And it says this: a pulsar emits a broad spectrum of electromagnetic radiation, which is detected with a receiver tuned to the neighborhood of frequency equals 80 megahertz. Because of the dispersion in group velocity caused by the interstellar plasma, the observed frequency during each pulse drifts at a rate given by df/dt equals -5 megahertz per second, which is kind of a weird unit. Per second, seconds. It's fine. A. If the interstellar magnetic field is negligible and omega squared is much greater than omega plasma squared, show that df/dt is about -c/x frequency cubed over plasma frequency squared, where fp is the plasma frequency and x is the distance to the pulsar. Part B says if the average electron density in space is 0.2 centimeters cubed, minus cubed, how far away is the pulsar, where 1 parsec is 3 times 10 to the 18th centimeters. So here's the problem. I'll put it over my face if you would like to pause and to try to solve it. One thing about this problem that I don't really like is that you don't need to know anything about plasma or pulsars to solve it. It's the kind of problem where they're like, show this mathematically. And if you know math, you can just algebra your way around the problem and get the equation they want you to get. But I figure we can talk a little bit about pulsars and try to understand actually what they're asking. So a pulsar is a rapidly rotating neutron star. They emit these pulses of radiation, which we observe at regular intervals, which is due to the object's rotation. And I'm sure I have a lovely little GIF that shows it kind of like a flashlight, where we only see that big flash of light when it's pointed directly at the Earth. But that beam exists the whole time. Pulsars were discovered in the late 60s by Jocelyn Bell Burnell, and the guy who won the Nobel Prize for that, who, like, ironically, I never remember his name. I'll put a picture of him with his name. And they called them little green men for a while, which I find really cute, because these pulsars, because they're physical objects with physical jets radiating from them, and they're rotating, so what's the word? Rhythmically, you see these pulses in the signal where it's just like exactly the same pulse every few seconds or every few hours, depending on whatever your pulsar is. And I guess they just saw the repeating signal and they were like, it must be aliens trying to communicate something. But they're pulsars. We see them all over. There's a couple thousand that we've mapped in our galaxy. So this question is referring to how these objects are observed. Something like this. What happens is that you have the radiation, which is electromagnetic waves, like photons of different wavelengths, being emitted from the pulsar. And those photons have to travel through the ISM, the interstellar medium, which is a plasma. Because the electromagnetic radiation is going to interact with the plasma, we receive the signal from different wavelengths at different times. You can imagine that higher energy photons will kind of just go straight through the plasma. They don't really care about what's happening in the interstellar medium, where lower energy photons will kind of start interacting with the ISM, and its arrival at our telescope or our faces or our eyes will be delayed. So what you're seeing are these like time delayed peaks, like as they arrive at the telescope. And the bottom here is where they correct for the time delay and stack the whole thing and be like, this is the signal from the pulsar. In the problem, the df/dt rate is the slowdown of the frequency's arrival at the telescope. And this is a really common type of figure you see when people are looking at pulsars. So the question is saying this rate of slowdown of the frequency's arrival at our telescope is going to be dependent on how long those photons are traveling in the ISM. The length of time that the wavelength is interacting with the plasma will dictate its arrival time. So if we observe the slowdown, shouldn't we be able to determine the distance? We know how slowed the pulses were, so we should be able to calculate from that how far away this object is, how long those photons were traveling in the plasma, which is kind of cool. Can you calculate the distance to an object based on the photon's travel time to you? Of course you can. So let's do it. That's what we're going to do. Okay, so we're going to solve this problem. Cool. Here's what they give us. They give us this frequency of 80 megahertz, which is 8 times 10 to the 7 hertz. And they give us df dt, which is minus 5 megahertz per second. So we get minus 5 times 10 to the 6 hertz per second. Cool. We're going to assume this is a normal electromagnetic wave because that's the section of the book that we're in. They give us this parameter here where the angular frequency of the wave, the electromagnetic wave that's traveling from the pulsar to our telescope, is much, much larger than the plasma frequency. And this makes sense because we're observing the wave. In order for the wave to propagate through the plasma, this has to be true. In math words, it means our K number is a real number and not an imaginary number, but that's beyond the scope of this. You can imagine the plasma frequency as like the result of the electrons and ions in this very hot plasma gas jiggling, right? They're hot, they're moving around. In order for the electromagnetic wave to go from pulsar to Earth, it has to propagate through this. If the plasma frequency, the jiggling of the electrons, is bigger than the wave that's moving through, the wave can't get through. The wave won't be able to transmit any information. So this is just a requirement stating that everything is normal because we observe the pulsar in our telescopes. So the first equation we're going to use is just the wave equation for a normal magnetic wave traveling in a plasma, which is this. The frequency of the electromagnetic wave will be equal to the plasma frequency plus c squared, which is the speed of light. So the speed of light plays a factor here because the electromagnetic wave is transmitting data and you can't go faster than the speed of light. That's the speed limit, times the wave number k squared. We also want to look at d omega dk because the group velocity of a normal electromagnetic wave traveling in a plasma is going to be d omega dk. So we just take this and do a little partial derivative business. We get 2 omega d omega. Sorry, my coffee for copying the problem. Over here, I guess. Okay, so 2 omega d omega is equal to c squared 2k dk. So here, d omega dk is equal to c squared k over omega. And we can solve for this. Let me change colors. We'll call this equation 1. That's not what I meant to do. And this equation 2. I can rearrange equation 2 algebraically to solve for what we have here in 1. So algebra time. Okay. It's at this point that if you've been in physics for a while, you will look at this and you will say, oh, I have to do the Taylor series expansion about 0 for this, which, let me switch colors again. For root 1 minus x squared, the Taylor series expansion is 1 minus 1/2 x squared, and we don't need any more than that. So I can rewrite that as ck over omega is equal to 1 minus 1/2 omega plasma squared over omega squared. And I can take that and put that back into 1. So actually Vg is equal to c times 1 minus 1/2 omega p squared over omega squared. Okay, but this is not what we want, right? The problem is asking for df dt, and what we have is a relationship between velocity and omega, not frequency and time. But that's fine because velocity is related to time, because you know velocity equals to distance over time. So time is equal to distance divided by velocity. So we can now rearrange this to say time is equal to x on c times 1 minus 1/2 omega p squared over omega squared to the minus 1 because it's in the denominator. We are trying to go to this little partial derivative. So now I'm going to do a little bit of calculus and take that partial with respect to omega, which gives you minus x over c times omega plasma squared over omega cubed. And to travel from angular frequency to frequency 2 pi, I think it's over here. I'm going to look that up. Hang on. I was wrong. No, I was wrong. I wrote it down earlier because I know I always get it wrong. So we get dt df is minus x on c omega p. Nope, I've already done it wrong. Plasma frequency squared over frequency cubed. And so to get to df dt, we get minus c over x cubed over plasma frequency squared. And that's the one in the book, right? Yeah, and that's the one in the book. So this is what I was saying. You don't really need to know anything about pulsars or plasma. You're just doing a bunch of algebra, but that's okay. What we learn here is that the shift in that measurement related to this plot we saw earlier is related to the speed of light, of course, how fast information can travel. It's related to the distance that light has to travel, the distance from the observer to the pulsar, and then the frequency of the light, which means that it's changing depending on the frequency of the emitted light, and the plasma frequency. Amazing. We did it. That's part A. I kind of just want to draw a little picture. So if here's our telescope, and here's the pulsar, the photons are traveling this distance. So this is the frequency. And they're traveling inside this big plasma, which has our jiggly electrons, which is our plasma frequency. So the more energetic those photons, the faster they will arrive here. The lower energy your photons, the slower they will be. And that will depend on what we see here, which is FP and X. Great. That's why we can use this to measure the distance between our pulsar and our observer. So let's do part B. So part B is just plug and chug, which again, this isn't a very hard problem, is it? I don't have the solution to the problem. A lot of times older textbooks don't have that little thing in the back where it's like, here's the answer to the odd numbers or whatever. I'm just assuming that I know how to do this. I'm sure the updated version, if it has the same problem, has the solution, but it's a really easy problem, right? So I'm not worried about it, which will become more embarrassing in the event that I've done this incredibly incorrectly. So it's kind of fun. Put some stakes in the game. Okay, so we want the distance to this pulsar, knowing that F is equal to 8 times 10 to the 7 hertz, and F, or dF dt, is minus 5 times 10 to the 6 hertz per second. And that doesn't look like a second. And we just solved for this little equation where we have dF dt is equal to minus c on x times f cubed over plasma frequency squared. So if we solve for x, we get minus c f cubed fp squared times 1 on df dt. Okay, so most of these things we know, but I want to talk about plasma frequency for a second. Let's switch colors. So the frequency of a plasma is dependent on the properties of that plasma. Here's one of the equation. Here it is. So the angular frequency of a plasma is equal to 4 pi times n e squared over m radians per second. So it's related to the mass of your plasma, the density of your plasma, and the charge of your plasma. So obviously 4 pi is a constant, and e squared is going to be related to m. So this is reduced to like a familiar, memorizable, like easy to calculate with plasma frequency, which is this. The frequency of a plasma is related to 9,000 times the square root of the electron density. So for our problem, they give us, what do they give us? 0.2 centimeters to the minus cubed. So that is what we will use in our calculation for plasma frequency. All right, so now we have all these numbers. We just plug and chug. So x is equal to minus 3 times 10 to the 8. I will leave the units as an exercise to the reader. It's just like seconds and hertz and stuff. But you should know that 9,000 has units, and so does electron density. So you'll have to keep track of those as well. Anyway, we have 8 times 10 to the 7 cubed over 9,000 square root 0.2 squared times 1 over minus 5 times 10 to the 6. And if you just plug that into a calculator, you get 1.9 times 10 to the 18 meters. Oh, I guess I'm using like 1 sig fig for all of this, right? Some people get annoyed by that. So we'll call this 2 times 10 to the 18. But they want the answer in parsecs. So x is going to be 2 times 10 to the 18 meters divided by 3 times 10 to the 16 meters per parsec, which gives us 66.6 parsec. Nope. 70 parsecs with 1 sig fig. That's the answer. I don't have the answer. I think that's the answer. So what we have done is we have taken these two numbers and determined the distance to our pulsar by looking at this chart and seeing how the signal drops, seeing the rate of delay of the signal based on the frequency of the received signal. we can determine the distance to a pulsar. That's pretty cool. That's really cool. Determining distances in space is really hard. And this is a really interesting way to do that, I think. I do think, though, if you have like a science-y brain, you might be looking at this and saying, like, really? Is that good enough? Are we just gonna assume that we have a good enough handle on 80 parsecs average density of the ISM from here to wherever that pulsar is? And people have been fighting about this since the discovery of the pulsar. Like, is this a good enough distance measurement? What if this is the best we have? So we just say it's 80 parsecs away with 100% error bars or something. A lot of things in astronomy are like that. I remember I was interviewing with someone to be my PhD advisor, and he did galaxy surveys, and he told me for his thesis, he just like looked at the images like with his eyes and was like, elliptical, this galaxy, a regular galaxy, like with his face. Because now you would write like a machine learning algorithm to sort through the images for you and like determine the minor and major axes and sort them based on whether they're elliptical or whether they're spiral galaxies. It's the old weird wild west of astronomy where they're like 70 parsecs plus or minus 70 parsecs. Let's think about one more thing as well. Imagine you have your pulsar and it's sending the photons, these are photons, to your observer. Here. What if your photons have to travel through like a big interstellar cloud, a big ISM medium? You're going to have like some magnetic field, right? Because you have all those charged particles that they're moving around and your photons are traveling through a medium with a magnetic field around it. This is going to have some distance. What's going to happen to your photons if they travel through a medium with a magnetic field? It's the Faraday effect. It's the Faraday effect, but in space. We don't notice the Faraday effect on Earth because the medium, the length of our atmosphere is teeny tiny. But what if the length of your interstellar cloud is parsecs and parsecs and parsecs long? The length, the Faraday equation was something like this, right? You have your magnetic field, you have the Faraday constants, and you have the distance. And in space, the distance is huge. So your light is going to be traveling through parsecs and parsecs and parsecs of the material, which even if the magnetic field is small, is going to contribute to a rotation of the polarization of the light. And so that's really interesting. And you can use the change in polarization of your light to study the makeup of interstellar clouds. That's really cool, huh? It's related. It's all related. The Faraday effect and stuff. So that was Coffee and the Problem. Take your little paper, put it in your little notebook. So see you next time. So I bought this book used, and it's annotated, which it doesn't bother me. I do like to read through textbooks and see what students were thinking or what they were confused about while they're reading it, as I'm also learning the same material to see if I'm confused about the same things. But I noticed that these are not student notes. Like, for example, the textbook is deriving something, and this person wrote, no, use Poisson equation and assume lambda is much, much greater than lambda dE. Like, he's decided that's a better way to derive whatever equation they're deriving. And I thought that was really interesting. So I found the name in the front, which is Glenn R. Longhurst. And I Googled it, and sadly, Glenn R. Longhurst passed away. It seems in 2021. I found an obituary, but he was a professor at Southern Utah University, and he has all these notes from his colleagues who are upset about his passing because he did a bunch of work in the irradiation of beryllium. And so now I'm thinking, I have the textbook of someone who taught this class, which is just really exciting and amazing. Like, what a find. When physicists retire or pass away, they have like hundreds of textbooks, right? And nobody really wants an old version of this textbook, although, as I said, like, it's plasma physics. It's not changing much. But I love that I found this on eBay, and I love that I have it. And I love that I have his notes inside of it. That's amazing. So that's just really cool. Yeah.